here we go. So I want to start off by giving you Biot Savart itself, help us to understand some of the pieces, and I will try to post this online so you guys, if you guys get stuck, you can go back and look at this again, okay? So here is Biot Savart. Do not write this down, just pay attention. And what does the dB stand for? No, it's a it's a very small amount of, don't think about it as a change of magnetic field, think about it as a very small amount of magnetic field, okay? A lot of pieces to learn in here. First of all, we have a cross product. We haven't done cross products in a little while, right? So let's talk about that. We should remember that if we had
R cubes.
what?
This says R cubed.
Yeah, no. This is the one out of Tipler. The reason for that is he has an R on the top and an R cubed on the bottom, yes? This is a little bit different. We're going to use Tipler's. I'll show you how to use that later on. Okay? So if this is J hat and this is I hat, remember this? What is I hat cross J hat with our hands? I hat, sweep towards J hat. Notice we have to sweep in this plane. We have to produce a plane that connects those two objects. Yes? I, J, K. Well, here we're going to sweep from DL to R hat. They're not, even though that doesn't have a hat on it, it's still a vector. This vector cross that vector. Never second vector cross first vector, or that gets you in the wrong direction. Now, you may wonder, this little IDL, it took me a while to realize, and I feel a little stupid here, but why it is that we have an IDL here, and that I isn't over here. We notice that these are constants, aren't they? The permittivity of free space and 4 pi, those are constants. Well, isn't I, if we have a conducting loop or a wire, isn't I a constant as well? Well, here's the problem. We do want to take the direction of the current, because current does flow in wires. And we want current, the direction of the current, and the direction towards whatever point, which is R. The problem with that is, isn't I a scalar? And if I is a scalar, we can't use it to do vector functions. So they came up with something different, known as the current element. If I take a wire, and we have current flowing through that wire, we say that this is a DL, flowing in the same direction as the current. Which means if the current is doing this, let's say that we have current flowing through this, well, the current doesn't change, but DL does change. The direction of DL changes as you go through the wire, but I does not change, it's a constant. This allows you to make current into a vector. Following what I'm doing there? All right. So now, a couple other things just to remind ourselves. If I were to take this, the antiderivative of little dl gives me what? L. Well, if I had a circle and all these little dl's, just like in Ampere's law, right? If I add up all of those dl's, what do I get? Then L equals 2 pi R. Looking around the room. We all good so far? All right. Other things that I'm assuming that we remember. We remember that if we have something set up where, and I'm just going to give you the actual letters we're going to use. There's going to be an X and there's going to be an R. Here's going to be our DL up here, coming out of the page or something. And here's going to be our point. So this is going to be R. And what does R equal relative to these two? Square root of x squared plus r squared, but I'm going to write it to the 1/2, because guess what's probably going to happen? Whenever you see that, there's probably going to be more of them, and they'll add together. We good? So far, everything is like stuff that we've done, yes? All right. You realize, is this, if r is always the same distance to the point, then that too is a constant. And the only non-constant you see is dl. Agreed? All right. What is this r hat thing? R hat, if we take a point, and let's call it Q. We're not going to be working with a Q, we're going to be working with a moving Q. So r hat would be, well, say to that point, well, to this point, that would be R2. R hat goes from the point from where you're taking your object to some point in question. R can never be negative. But you say, what about R hat? R hat points in the direction of R and has a value of 1 and no units because it is a unit vector. Now, how does that work out? This took me a long time to figure out because actually what Tipler does is he takes R hat and he actually puts in ijk for I hat. He puts in ijk for this other stuff, and he actually does full-blown explicit calculations. They're not horrible once you get things set up, but you have to be able to do your cross products. Well, what is R hat? Number-wise. This is the only way I was able to come up with it to make this easy. What is that? That is the vector R. And vectors have both and direction. Where that's the magnitude of R, that is the vector R, and that's R hat. Magnitude and direction. So if I wanted to know R hat, what are the units of R? Meters. What's the units of the magnitude of R? Meters. What's the unit of this? Nothing. Meters divided by meters gives me nothing. Now how, yes sir?
So like when you multiply that times DL, does it change the value of DL?
No, just gives it a direction. It's literally just so that you can do the cross product and know where things are pointing explicitly. So how would I calculate this? Well, let's just say that I have, I will make this obvious. We'll do something super easy. This is 4 meters I hat, 3 meters J hat, and this would be R. Well, the magnitude of R equals 5 meters. And I wrote 4. That's okay. Stop it! Okay, it just does its thing. Okay, so we agree with that, yes? That the magnitude of R is 5 meters. Well, if I try to figure this out, well, I could say that R hat equals 4 I hat plus 3 J hat, easier to read, meters. And the magnitude of R would be 5 meters. Did I put it in the right spot? No, I need that on the other side, sorry. Equals R, which is 5, times R hat. The vector equals magnitude and direction. So what does that equal? Equals 4 divided by 5 I hat plus 3 divided by 5 J hat meters equals, oh no, meters divided by meters, there you go. If you square that, plus the square of that, take the square root, you get 1. 16 plus 9 gives you 25, divided by 25 gives you 1. This is a unit vector with no units and a size of 1. Which way does it point? That way, exactly along R. We're going to do that again. I get that you're like all going, whoa, there's gray matter like on the inside of your cranium right now. Okay? Remember, magnitude and direction, and the magnitude is how long the vector is, and the direction is R hat. Okay? And again, we will do that in the future. How are we feeling so far? Not horrible, but it's a lot of stuff. Now, the last thing that I need us to see, for later on that we do this in full blown, is we're going to figure out the direction of B. Oh, one more background thing. And this is the one that's going to make our lives phenomenally better. Okay? You're all going, something's got to be better. Well, yeah, let's use the same one we just did. Let's say an object has a, let's use R again, and R equaled 5 meters, and we'll just call it R hat that direction, right? And this is 4 I hat, 3 J hat, Okay? Well, would you agree that R equals in vector notation, it says go the direction of x as a vector, go the direction of y as a vector, and that your sum will be the total of those two vectors. We agree? Therefore, dB, all of dB, equals we agree? I'm just saying the vector, your x component, your y component, will give you your total vector. If you add them as vectors. Now some of you might be saying, what happened to square root? That's for magnitudes. This is saying if you're doing arrows, x, y, vector. This is your x component, your y component, and your, I'm just going to call it r just to make that easy, yes? So, if I know my x component, and I know my y component, doesn't that give me my vector? And you could even just say this. Isn't that really what we're saying? We're just expressing it in I hat and j hat. Yes or no? Okay. If that is true, then this too is true. And I do have to put the vector symbols over there, or the operation is not true and you need Pythagorean theorem. Is that not also true? That says, if I add up all of the total vectors, if I add up all of the little magnetic fields to get the total magnetic field, I can find that by adding up all the x components of the magnetic field and all the y components of the magnetic field. Yeah? So therefore, B equals and this, my friends, is going to make your life better, though you know not how, as of yet. Now, let's do one more thing, and then we'll start. We'll give you a 5-minute cleansing period. Okay. I'm going to show you the example that we're going to do. And I apologize. This is supposed to be 3-dimensional, and I have 3-dimensional objects to help you out. So let's imagine that we have a loop of wire. And instead of me drawing it this way, I'm going to take it and tilt it this direction so we can see it more 3D. Okay? So if it turns, you see how it's going to shrink a little bit in the... So I'm going to do this. Okay? The current is flowing this direction in the wire. So that's the actual direction of little dl. And here it's going dl. And this is into the page. This is out of the page, so it's going this direction. Okay, then I'm going to do this. Well, actually, let me see if I can help myself here. If I had a little bit more time, I could make this thicker and that thinner, but it's going to have to do. So we're going to call this one of the axes. Here's my little help sheet here. And then we have another axis here. And then we have this axis coming out of the page. You see how that one goes into the page. I didn't connect it, but yeah. Okay, you kind of follow what's happening? This one's coming out of the page. Yes? So it looks like this, and that main axis is coming out of the page like this. We follow? We have current going this direction around. And we're going to take a point P. We're going to say this distance to that is x. And we're going to say that this distance to the radius of that ring is big R. Well, we would like to find the magnetic field at that point due to all of it. And we're going to have to add all of them up to get the total magnetic field. So I take my little current element here, which is going that direction. R goes from there useful later on. So that is going to be r. And that's also, by the way, the direction of r hat. In the direction of r with a unit vector. Are we good? So, it says the direction of b, of the little dB, due to that little dl, that little current element, is dl cross r hat. dl cross r hat. So what we have to do, we make a plane of those two. So if dl is going this direction, this is the direction of r, and we have to sweep in that plane. We can't sweep this way. It has to be dl and r. So we take our fingers, we lay our hand on r. Lay your hand on r. Sweep your hand the direction of dl towards r. And see how your thumb points that direction? Which is perpendicular to both of them.
When you said sweep from DL to R, not R to
But I'm setting it up. I could go that direction or this direction. See, dl, cross r. Because since I know this is r, I'm going to be in this plane. dl, cross r. dl, cross r. Now, you are having trouble seeing this, aren't you?
Most definitely. Yeah.
Yes, you are. Okay, and we will deal with this in a second. So, you're going to have one from this side, and can't we all figure out what r is? From these letters? And we figure out that this is theta. And you might wonder, well, is this theta right here? And I'm going to tell you that's hard to see. So we're going to do this. We have visuals. If this is the perpendicular, and I move r up, this is theta. See how I did that? You can actually just do this. You know, moving your thumb. This is R, that's B, and you can see what angle you're changing. Once again, there's the perpendicular. Do we see it? Now, there's going to be one from down here too. And once again, there's going to be a vector addition here. That would be very hard to see, wouldn't it? But Mr. Murray has visuals. Make sure that we can see this on the video. Those of you in the back, if you need to stand up, those of you in the front should be able to see where you're at. If you need to move to the side, there's lots of room over here. And yes, this is a big deal. You need to visualize this. So let's imagine that we have, I'll use my pens here, pencils and so forth. We're going to say the current is flowing this direction. So I'm going to put a pen there. We're Yoda. We have a pen going that way and a pen going this way. So the current is flowing this direction in the loop. Now you should already know that if the current is flowing this direction in the loop, we sweep our fingers around and the magnetic field should be pointing that direction. And as we get very, 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 very far away, you should think, well, it should probably go to 0. And it would be strongest right here. That should be logical. And if you look up here, you see that r squared. The farther away you get from the loop, the smaller the magnetic field. But this is how it works. Can you grab me those magnets? Right here. Okay. Ta-da. Now, let's talk about what we have here. Here is DL. Here is R. And yes, with a little bit of time, I could label these, and that might be useful, right? So here's DL. Here's R. I take my hand in the direction of DL. You should all be doing this. DL slash R gives me dB in this direction, which is perpendicular to both of them. DL cross R gives me that DL cross R points this direction. Agreed? On this side, DL is now pointing towards me. DL / R, my thumb is pointing this direction. Do we follow what I just did there, yes? That's easy to see, isn't it? Now, looking at these two vectors pointing away from each other, this one is due to that side, this one's due to that side. And what do you notice cancels? The horizontal components, which in this case would actually be the vertical components, wouldn't they? And you see how in this case, these components in the direction of where we're going, those add together. You see it? Cancel, add. And could you imagine that if we took this and we rotated it like a pyramid, that would occur for every two on opposite sides? Yes? And if we did this, if I took them and without changing these, can you imagine as I go like this? Only imagine that these are moving in, right? So they're moving in here. Do you see how the vertical components are now adding up until you get to the very center, and they're all adding up and there is no cancellation? You see it? As I move farther away, moving farther away, moving farther away, moving farther away, you see how they're getting more and more in opposition. And as R goes to a very long distance, which we will call infinity, there will be no magnetic field at infinity because all they are doing is opposing one another. Now, yes, I know that it's much easier for me to do it this way, but you have to learn to visualize this on paper. And this, as you know, is one of the most difficult parts of magnetism, isn't it? So here we go looking on the paper. And it actually turns out we're actually almost done. Once we figure that out, we're almost done. So if you notice here, see theta? I go, L is coming out of the page, so I put my hand out of the page, cross R. You see how it's pointing this way? You see it a little bit now? So we have that going this direction, perpendicular to R, and that's our vertical. And we all understand why that's theta now? And likewise, we'll have one on the other side that will cancel as well. I may not have drawn it as well. So here we go. There we go, that's better. Those should be perpendicular. There's also theta. This is dBx. That's dBx. We don't need that anymore. And can you see that these vertical components cancel, don't they? Would you agree that all of the dy's will cancel as you go around and you wrap this thing around it? Yes? But the x components will add together. So now we need to figure out what this is. This is going to be dBx. Sorry, that's just dB. My apologies. Not dBx. That's actually dB. Okay? Well, if that's theta, is this dBy, is that sine or cosine? That's cosine. Therefore, this must be, so this is dB sine theta. I will pause to make sure that everybody's following what I did there. Yes? I'm saying for just that one. Yes? All right, so here we go. I guess I can finish this off very, very quickly. We see this. What do all of these equal? 0. And we just have to add up. This is what Tipler does with words, but I've just made it explicit. Explicit means there's no doubt. I don't have to go, well, we're going to kind of figure it this way. No, this makes it clear. All I have to do is add up all the x components, don't I? So now let's do that. So we have, this is dB. But dBx will be this. And now I'm going to take all the constants, I'm going to slap all the constants, well actually, for a second, they're almost all going to be constants, so just hold on. So I dl over 4 pi r squared. I'm going to get rid of this now. We dealt with it. Didn't we deal with it once we did this? Once we do this, we have found the cross product and we no longer need it. So it's just that, but it's dBx, which is going to be sine theta. Yes? We got rid of the cross product by splitting it up into its components. We figured out that all the y components equal 0, and the x components add together around the entire thing. We good? So, let's go ahead and figure out what we need to. Do you agree that this, and this are all constants? Theta is not changing, r is not changing, I is not changing. So now, I'm actually going to add them up now. Or no, yeah, let me just take out all the constants. No, I already did sine theta, and now I have this pesky dl. Do you agree all of those are constants, yes? Well, I am now going to find the net magnetic field. The net magnetic field will equal constants come out, and what is the integral of dl? Just L. And what is L for this? 2 pi big R. So this, and I'm going to start just kind of pointing at stuff. This is 2 pi big R. Yes? What is R squared? What is R? We said that R is, I already canceled it out, so R equals x squared plus R squared to the 1/2. Good? And just by the way, what is the sine of theta? This is where I made my mistake. I felt really stupid. What is the sine of theta? For sine is opposite over hypotenuse. Opposite over hypotenuse. Oh look, another r. So that's not just r squared, it's actually r cubed. So now let's put it all together. B equals mu naught, that's the worst mu naught in history. Sine of theta is r over r. And I'm just going to do it this way and we'll, wow, that's just hard to pronounce. One thing, we have mu naught I r over r, that's sine theta. And we have 4 pi r squared. The dl gives me 2 pi big R. Yes? And we know what R is, so we get B equals. And by the way, he keeps the 2 pi. I don't know why he does that, but he keeps the 2 pi and the 4 pi. I would cancel them out, but for some reason it's important. I think it's to show you how it looks like Ampere's law a little bit. So I'm just going to put it in there. So 2 pi mu naught I r squared, yep, over 4 pi. And r is x squared plus r squared to the 3/2. Oh, my apologies. You see that? It's an arrow. That's not a vector. Well, now it is. And that, my friends, is Biot Savart. Yeah.
So is this essentially like Ampere's law, but in like 3 dimensions, like with a current that's like perpendicular?
I'm not exact, I know that Ampere's law is valid in all cases. And I'm not sure, I kind of think that Ampere's law may be like a more generalized form of Biot Savart. I can't answer that. I'm just being honest. That's the high school question I can't answer. But if we look at these things, kind of interesting. What if x gets really, really big? Would you agree as x gets big, then r is irrelevant? So as x gets really big, x squared goes to infinity, then this, oh, that's supposed to be squared, right? Yeah. Approaches just x squared. So to the 3/2, right? This actually becomes a very large number, and this becomes a very small number. Remember how they went like this? And they began to cancel themselves out. What if x goes to 0? If x goes to 0, then this becomes, approaches just r squared, and this whole thing just becomes r squared to the 3/2. You agree that that just becomes r to the 3rd. And that just gives me an r, and that just gives me a equals mu naught I over 2. There's supposed to be a pi there. Why did I miss a pi? I will look at that. I obviously made a mistake because it's supposed to reduce just to a loop of wire. No, what am I saying? It's a loop of wire. It's not. I was trying to think about the long wire. I'm completely stupid. Sorry, YouTube. Okay, it happens. So the biggest thing that helped us here, we are going to visualize this with those rods many times, aren't we? Okay, you understand why this is a little bit of a bugaboo? This is a bear, isn't it? Okay, bugaboo. You hadn't heard that word before. Bugaboo. That's an old expression. It says something. Yeah. It's kind of like the man patch. It tells you something. I'm seasoned. Barbecue. Okay. And you see how that made it do you see how that made it a lot easier? Right? Okay. So I suggest, it is 11 o'clock, so pause, we don't need to